This is the audio lecture for part 1 of chapter 6 and 7, reliability and validity, and criterion reference tests, cut scores, reliability, and validity. There are several learning objectives for these two chapters, which you can read on this slide and the next few slides. Next, we're going to talk about the concept of reliability. Reliability relates to the consistency or repeatability of scores resulting from the application of a testing procedure. Reliability is also the degree to which repeated measures of the same trait are reproduced under the same conditions. What that means is a measure is reliable if one is able to obtain the same score each time the instrument is administered to the same person under the same conditions. So that would be me giving you a test and you scoring the same on it multiple times on the same day. Then that's a reliable test. Reliability can also be described as consistency, dependability, stability, or precision. The next concept is the concept of validity and relevance. These are similar to reliability, but very distinct. Validity is the degree of truthfulness of a test score. In other words, does it measure what it purports to measure? It's dependent on two characteristics. It's dependent on reliability and relevance. Relevance is the degree to which a test pertains to its objectives. So, for a test to be valid, it must measure the particular trait or characteristic consistently, and it must be related to the characteristics reportedly being measured. So relevance is the degree to which a test is measuring to its objectives, but validity is the measure measuring that trait or characteristic consistently. Next, we have the concept of objectivity. So objectivity is a special kind of reliability. It can be known as inter-rater or intra-rater reliability. So those are two distinct things. Inter-rater reliability is consistency between two or more independent judgments of the same performance made by two or more raters. So inter-rater reliability, an example of that would be if two people are watching, let's say, a dance performance, and they're grading it on a rubric. Is there consistency between those two judges and their scores of that same performance? And then we have intra-rater reliability. So intra-rater reliability is consistency in scoring when a rater scores the same test or performance two or more times. So if we take that dance competition example, if I watched it, if I was the judge or the scorer, and I watched it today and I scored it on a rubric, and then I watched that same performance, let's say it was videotaped, if I watched that same performance 2 weeks later and scored on the same rubric, is there consistency in that scoring? So intra-rater is consistency on the same evaluator or rater on the same test or performance multiple times. An inter-rater is two different people judging the same performance. Okay, so we will talk more about those terms, but it's important to understand those concepts. So objectivity is looking at that inter and intra-rater reliability. So an objective test has a higher inter-rater reliability. So there's more reliability when two or more independent people are judging the same thing. So with reliability, we can look at it through a couple different lenses. We talked previously about a Pearson product moment correlation coefficient, and that can be used to provide evidence of a test's reliability. So part of reliability is there are observed, error, and true scores. And these are theoretical concepts which will help us understand reliability. So if we're looking at it from an equation standpoint, our observed score equals our true score plus our error score. If we remember, we had a graphic in chapter 4 that kind of demonstrated that. So what do we do with that reliability concept and apply it to data? So if we look at this data table here, we have systolic blood pressure recordings for 10 participants. We can see in the left-hand column, we have our participants 1 through 10. Then we have our observed blood pressure, okay? Each participant has an observed blood pressure, but it is possible to have an error. So the observed score is not necessarily the true blood pressure value, but that is what we measured. So if we put on the blood pressure cuff, we measured the systolic blood pressure of participant 1 at 103. If we look here, we also have a true score and an error. The true score is impossible to measure, but it's here as an example, okay? An error score can occur for any reason that causes your observed score to be different from the true score. So for example, maybe you missed the first beat of the systolic blood pressure when you were taking it. Maybe your calibration is off a little bit. So there's a lot of variables that can create error. So our error is noted in our right-hand column. Our error score can be either positive or negative. So if we look here, we're taking our observed blood pressure, which is equal to our true blood pressure plus our error score, okay? So when it comes to observed, error, and true scores, each person's observed score, like we talked about, is the sum of the true score and the error score. Again, the true score theoretically exists, but it's impossible to measure. Every test that we do has some level of error to it. How they get true scores is the theoretical average of an infinite number of tests where one doesn't get tired or learn from practice. So it's a statistical score that they can calculate, but you can't actually measure it yourself. And then that error score results from anything that causes the observed score to differ from the true score. So we gave some examples previously, but if we think about, like, let's say skin fold testing, the calipers have a set error to them versus doing bod pod has a different error rate versus doing a DEXA scan has a different error rate. So there's a lot of different things that can contribute to our error score. So now we get to the math part of reliability. It is a variable that we can measure. So a test is said to be reliable, which is denoted by R subscript XX, to the extent that the observed score variation is made up of true score variation. So the reliability is the true score variance divided by the observed score variance, is what all of that means. So S squared subscript T is the notation for true score variance. S squared subscript 0 is the notation for the observed or total score variance, and the S squared subscript E is the error score variance. So you don't need to memorize that, but that is what the standard equation looks like if you come about it. So reliability equals the true score variance divided by the observed score variance. So our theoretical conclusions of reliability are our observed score variance equals the true score variance plus the error score variance. We can't ever know the true score, but we are able to estimate the error score variation for a set of scores. So these can be through a variety of methods. But our biggest thing is when we're looking at our reliability coefficients, they range from 0 to 1. And the closer you are to 1, the better the reliability is. So a desirable level of reliability is generally 0.8 or higher. When we're looking at different tests or different assessments, the longer an assessment is, the more reliable it tends to be compared to a shorter assessment or test. Part of that is we have more data points to look at the reliability. But again, we can never know the true score. So we have to use the observed score plus the observed score and the error score in order to get our reliability. So to calculate the reliability coefficient, we look at our interclass coefficient, which is based on our Pearson product moment correlation coefficient, which we talked about in chapter 3, and then an intra-class coefficient, which is based on an assessment or a statistical test called an ANOVA. We skipped that chapter because the ANOVA isn't super applicable to what we need to do in this class, but just know that that's how the reliability coefficient is calculated. Within interclass reliability, we have 3 different components. We have a test-retest reliability, equivalence reliability, and split halves reliability. We're going to talk about those in depth coming up. Test-retest reliability is when a single test is administered twice to the same participants. These scores of the separate test administrations are correlated using the Pearson product moment correlation coefficient. So that would be like administering a fitness test today and the same fitness test tomorrow and looking at how the scores are related. We would expect similar scores between those 2 time points without an intervention. If the time between the testing occasions is longer, such as days, the test-retest reliability is often called stability reliability. So it's stability reliability because that measure is consistent or stable across time periods. So if we look at this table here, we have our participants in the left-hand column, and this is looking at sit-up performance. Trial 1, we have the different scores for all of the participants, and then let's say the next day they did trial 2. As we can see, the scores are similar. But then we can also calculate that test-retest reliability score. So we summed the scores, took the mean, the standard deviation, and the variance, and then we used that previous equation that we talked about earlier to calculate our reliability, or the R, which equals 0.927. As we remember, a reliability score of 0.8 or above is considered strong or ideal. So this is a strong reliability score. While test-retest is administering the same test to the same participants, we also have something else, which is called equivalence reliability. This is looking at 2 parallel or equivalent forms of an exam that are given to participants. To ensure parallel, a sample would take both tests. So for example, if you had a test form A and a test form B, half the test takers would take test A first and then test B, and the other half would take test B first and then test A. The results would then be correlated between those two test scores for each participant. So the scores on each exam are correlated using the Pearson product moment correlation coefficient to determine the level of agreement between the two exams. So we're trying to see, is test A reliable to test B? So again, the same participants would take both test A and test B. But half would take test A first and then test B, and the other half would take test B first and then test A. This is to ensure that there's not like a learning curve as you're exposed to each test. Similarly, we have split halves reliability. This is different from our equivalency reliability. So in split halves, a single test is split into parts. So if I have a test, let's say it's 50 questions, I would have half of the participants do all of the odd questions and the other half do all of the even questions. And then I would look at the reliability between those that answered the odd questions versus those that answered the even questions. This is done when we can't administer separate tests or the same test twice is not an option. So we don't have the time to be able to have them do both a part A and a part B. So we have half of them do the odd questions and half of them do the even questions. But then we want to analyze to make sure there's reliability between the odd questions and the even questions. Those were all inter-class reliability measures, both the split halves, the equivalence, and the test retest. Now we're going to talk about intra-class reliability. So intra-class allows you to estimate reliability when scores from more than two trials aren't available. This also addresses the consistent difference between the means issue that can be seen in inter-class models. So we can have an issue because there are mean variations in our inter-class that don't exist in our intra-class reliability. We can also calculate the index of reliability. This is a theoretical correlation between the observed scores and the true scores. So we talked earlier about how the observed scores equal the true scores minus the error scores, right? So to do our index of reliability, we would take the square root of the reliability coefficient that we calculate. We can also calculate the standard error of measurement, sometimes abbreviated as the SEM. The standard error of measurement reflects the degree to which a person's observed scores fluctuate as a result of errors in the measurement. The SEM is the standard deviation of the errors of measurement around an observed score. So we can look at the equation here, which is SEM equals S, or our standard deviation of the test results, times the square root of 1 minus the estimated reliability. I'm not going to make you calculate this, but it is just something I want you to be aware of in case you come across this notation. Lastly, for this video, there are a variety of factors that can affect reliability. These include things like fatigue, practice, participant variability, time between testing, circumstances surrounding the testing periods. Is the test an appropriate level of difficulty for the testing participants? Precision of the measurement, and environmental conditions. So if we're talking about, let's say, a push-up test, If this push-up test, let's say it was administered after 3 other fitness tests, the participant might be fatigued, so they might not do as well. If they've been practicing push-ups for 2 weeks prior to taking the push-up test, they might score better. Participant variability, maybe the person didn't eat that day, so they're not feeling as good. Or the time between tests. Maybe they took this test, it could be time of day or time between testing sessions can affect the time between testing. Circumstances surrounding the testing periods, maybe things like the person is just not feeling well that day, or they had a lot to do before they took the test. That can all have an influence on the reliability. Is the test difficult enough? If we give a push-up test to elementary school students, yeah, it's probably difficult. If we gave this test to athletes that do CrossFit 5 times a week, is this push-up test really the most appropriate test, or is it too easy for them? Precision of the measurement, if we use our push-up test example, we're just counting reps. So are we having some sort of standard where they have to hit their chest at a certain level? Or are we just counting every time they bend their arms? And then environmental conditions. Is the gym really cold? Is the floor too soft or too firm? Things like that can all affect the reliability of the test. So know what these factors are and know how they can influence the reliability. We're going to stop this lecture here, and then we'll talk more about the validity in our next video.